This is the first, this is 2011 8B, and 2011 8B we're doing the following. A square lamina PQRS of side 60 centimeters and mass M can freely turn about its horizontal axis through P. P is here. Horizontal axis, perpendicular to plane lamina. What does that mean? It means it can sort of move like this, where it just rotates around. Okay? Now that we know what that means, we're next going to go on to the lamina is released from rest when PS is horizontal. So PS is horizontal. Find the angular velocity of the lamina when PR is vertical. Now guys, it's a square. It means the centre of gravity is going to be dead centre, yeah? Now, the problem is, it will only rotate if the centre of gravity can fall further. So, if I write it down in its diagonal position, okay, so what I'm going to just do is just going to take another screenshot here. I'm going to show you what I mean. Okay, just give me a second with this. Okay, so what happens is, here it is in its horizontal position, okay, and look what happens when I turn it vertical. Okay, what happens when I turn it vertical is, you can see that the centre of gravity at the moment, the centre of gravity is a distance, what we call this distance, it's a side 60, isn't it? So if that's off side 60, that's 30 and 30, and we did it in terms, so I'm going to do it in terms of meters, okay? So that's going to be 0.3 and 0.3. Do you understand that it's 0.3 below PS, yeah? Now, if I was to do a right angle triangle, and I was to find out what the length of PG is, so this is P to G, okay, it's going to be 0.3 by 0.3, we're going to do Pythagoras' theorem, and when we do Pythagoras' theorem, we're going to get that PG is 0.3 root 2, okay, when you do Pythagoras' theorem. So, what happens is, if you can just look up for 1 second, this will fall because the centre of gravity, it will rotate, and what happens is, it's fixed at P, so if I superimpose this over here, it doesn't work that way, but what you would be able to see if I put P at the same level is, the centre of gravity has actually fallen a small amount. The centre of gravity, if the centre of gravity falls downwards, that's what causes the rotation. Okay? So that's what we're looking at. Now, what we've got to do next is rotational energy. Rotational energy equals will be the loss in potential energy. Okay? Rotational energy is a half inertia times angular velocity squared, and that's going to equal mgh1 minus mgh2. The difference in height of the difference in height of it before turning and after turning. Okay? So the difference in potential energy. Now that we've established that, what we're going to do next is we're going to talk about a normal lamina, a normal uniform lamina. Okay, so it's a square, and here it is here. Now, if there's two axes on the square, we can go through this way, and we can go through this way. Two different inertias. Okay. Now, these ones, unfortunately, aren't perpendicular to the plane. They aren't perpendicular to the plane. Okay. So what we have is, we can call this XX, YY. Now, if you read up on your notes, I lamina around the centre, okay, we call the centre G. I lamina is a third ml squared. That's the formula. Now, a third, what's M? M is M, isn't it? Is that what it says in the question? Mass M. Yeah. Now the length, remember this is for a length of 2L. 2L equals 0.6. What does L equal? 0.3. It tells you this in your notes. This is a formula for length 2L. 2L equals 60 centimetres, L therefore equals 0.3. So remember to change that to 0.3 squared. Okay? There's two axes. There's X, X and Y, Y. That's two different rotational axes. Okay, so we have a third ml squared, and then we have I, Y, Y is also a third ml squared. Now, what we're going to do next is we're going to do the perpendicular axis theorem. Does anybody remember the perpendicular axis theorem? Okay, perpendicular axis theorem. And what's going to happen is, if there's an IZ equals IX plus IY. The perpendicular axis is equal to the two other axes added together. So, the inertia going into the plane. Now, I'm talking about the where's the object? Whenever we can do it this way. If I was to rotate it around its centre like this, that's what we're talking about. We want to get it so it's like you have your finger in the middle of G and it's rotating around on the table. That's what we're trying to get at. Okay? So what we're looking to do here is we're going to do the perpendicular axis theorem, and it's around G. So we're going to get IG equals IX, which is a third ml squared plus a third ml squared, which is going to give us 2/3 ml squared. Okay? Now that that's done, okay, it's going to be 2/3 m times 0.3 squared. Okay. Now, we currently have, that's its inertia. This part here is its inertia when it's rotating around its own centre. We're not rotating around the centre. Where are we rotating? We're rotating it around the corner P. This is where we're rotating around. So what we got to do next is we got to do the parallel axis theorem. Okay? So G is parallel to the axis P, but we need to change it. So we're going to do the parallel axis theorem. Now the parallel axis theorem reads this: that IP, what we're looking for, equals IG plus MD squared. IG is what we got a second ago, 2/3 m times 0.3 squared. MD squared relates to the mass of the lamina, also relates to the distance away from D. Okay? Now, what I said earlier is when you do Pythagoras' theorem, and this part up here, before you square root it, it's going to be 0.3 squared plus 0.3 squared, and that gives you 0.18. The hypotenuse squared is 0.18. Therefore, this distance from here to here, this distance D is 0.18. So m times 0.18. Add them together, and what you get is IP ends up to be 6/25m. Okay? Now, next thing we got to do. We've figured out, if you go back to the start of your equation, you figured out this part here. This is the first part done, because you know what I is. You now got to figure out your height loss. So how are you going to figure out your height loss is what you're looking to next, okay? So, what I said was, at the start, so 1 second. Yeah, work away. Okay, at the start your centre of gravity is below. At the start your centre of gravity is below PS. Okay, so to calculate height loss, the start centre of gravity is at point G. The point G is located 0.3 meters below PS. So PS is here to here, and we know that G is located 0.3 below this axis, 0.3 below P. At the end, it's going to be located a larger distance underneath it. So we'll see what this is now. So when we rotate it underneath, It's now going to be directly underneath P, and this distance we know already is the hypotenuse of the triangle from earlier, which is going to be 0.3 root 2. So this is 0.3 root 2. Okay, so it's going to be 0.3 root 2 below P. Okay, so we're going to find out the drop in height. So the loss in height is going to be loss in height is going to be 0.3 root 2 minus 0.3. Okay, so that's the loss in height. So what we're going to do is go back to our original formula. A half rotational energy, a half IW squared equals mgh1 minus mgh2. We can factorise that and turn that into mgh1 minus h2. And this here is exactly what that is. Your old height, sorry, your second height, so you're going to calculate the drop in height, okay? So the drop in height is this one, take away this one, so you want to find out the drop in height, okay? So what we're going to do is a half I, now I is 6 over 25m, 6m over 25, omega squared equals mg 0.3 root 2 minus 0.3. Let's see what we can cross off both sides, okay? So we can cross the m off both sides. We can use gravity equals 9.8, multiply 9.8 in by this number. Okay, so we're going to get 9.8 brackets 0.3 root 2 minus 0.3. What we get there is 1.218. Then we're going to multiply that answer by 2. And then we're going to divide that by 25 over 6. Or so we're going to divide it by 6 over 25 and we move that over to the other side. Okay, so we'll just double check this again. Oh, sorry, we can leave it in terms of G if we want. So look, we're just going to divide this by 9.8, leave it in terms of G, and it's 1.0355. So omega squared equals 1.0355 G, or if we were to multiply by 9.8, what we'd have there is 10.15, okay? We're going to square root this, so W square root our answer, and what we get there is 3.19 rounded off. So the angular velocity is 3.19 radians per second. Okay, and that's what we're asked to find. We're asked to find mass m, find the angular velocity, done. Find the period of small oscillations of a compound pendulum, and hence or otherwise find the length of the equivalent simple pendulum. Okay, so mass m is attached to the r, so the whole setup has changed. Okay, so what happens this time is we're told that a mass r is attached. Okay, so the mass r is going to be attached down here. This is r, this is p. Okay, r and p. So we have mg coming down. Okay. Now, the inertia of the lamina on its own, from the last part. So the inertia of the lamina around P, okay, we call it IP of the lamina, was 6 over 25m. Or 6m over 25, excuse me, okay? Now, this doesn't include the inertia of the new mass, so we're going to do the inertia of R. IR. So, inertia of mass around P. Now, the inertia of a point mass is mr squared. Okay? And that's around P. So what we're going to do with this point mass, so this is the inertia of the point mass here. Okay? And what's going to happen is we're going to get mr squared. And we know that it's going to be m times r squared. Now, r is going to be, we have to figure out what is the distance r. The distance r is from P to r, this distance here. Okay? And that's going to be 0.6 squared plus 0.6 squared. So we need to find out what PR is. Okay? So PR is PR squared equals 0.6 squared plus 0.6 squared. And what we're going to get for PR is we're going to get so PR squared ends up to be 18 over 25 when you put that into your calculator. So r squared, or PR squared, because this is the distance we're looking for r, is going to be 18 over 25. Okay? And that means I equals 18m over 25. Now that's the mass around P. Now, the total inertia, therefore, the total inertia is going to be I total around P equals I of lambda only plus I point mass. And what we're going to get when we add them together is we're going to get 6 over 25m plus 18m over 25. Okay? And then we're going to get I total, or I around P total, is going to be 0.96 m. Okay. Now, question asks us specifically about the period of a compound pendulum. The period of a compound pendulum, T, equals 2 pi square root of I over mgh. I is 0.96. M is the mass of the full system, or capital M as we call it. Capital M now equals 2m, because the lambda is mass M. The lambda is mass M. And the point mass is also mass m. So look, the lambda is m, and the point mass is m. That makes 2m when added together. Okay? We have to find out what h is. Now let me tell you what h is. Okay? What h is h is the distance from P to the new center of gravity of the system. So the old center of gravity was located here. Okay? And that was until the point until we attached the point R. Now what R in effect does to this system is it lowers the center of gravity towards R. Okay? So we have to find out what the new system is. So what we always say to find this is moment of sum equals sum of moments. Okay? So technically a moment is force by distance, or weight by distance. So the moment of the sum is going to be 2mgh. 2mg, that's the weight of the system. The distance we're going to describe as h, which is distance to the new center of gravity. Just let n be the new center of gravity that's acting downwards, okay, of the system. So that's going to be 2mgh. Sum of the moments, well, the mass m, okay, and this is going to be the mass of the lamina, is going to be 0.3 root 2 from the last question. So remember, from the center of gravity, this is for the lamina. the lamina is a distance 0.3 root 2 away from the centre of gravity, so it's going to be mg root 2. So mg 0.3 root 2. Okay? Then the next one is going to be the distance of P to R. Distance of R, which is the point mass, from the rotational axis P, which is going to be mg is its weight, and its distance is 0.6 root 2. Or 0.6 root 2 from earlier is what we would have got if we square rooted d from earlier. And if you remember d from earlier, it would have been, it was 0.6 squared plus 0.6 squared in Pythagoras' theorem. Okay, so we'll just do this here. 0.6 squared plus 0.6 squared. Square root answer. And if we divide that by root 2, 3 over 5 root 2, or 0.6 root 2. Okay? So there is there 0.6 root 2. Now, this is the point mass. Next thing, we're going to add everything together, cross off the m's and the g's. And we're going to find out is that 2h. Put this into the calculator, or no need, 0.9 root 2. Then h therefore is going to be equal to, we're going to say 9 over 20 root 2, and you put it into the calculator. 9 over 20 root 2. Now finally we can figure out what the pendulum is by using this value here. Okay? So we go back to what we started off with, and now we've completed everything we need regards the pendulum. Okay? So we have all our information for the pendulum, which we will do now. So T therefore equals 2 pi I, which is 0.96. Now it's 0.96 m. Just remember that from the last question. M is going to be 2m, and then G is still going to be G, and this is going to be 9 root 2 all over 20. Now you can put all of this into the calculator if you want. Cancel off the m's, and what we can do is we can put it all in. So we can say square root bracket square root 0.96 divided by 2 multiplied by 9.8, which is what G is, multiply by bracket 9 root 2 divided by 20, close it over, and you can see here is going to be 0.27. Now we have to multiply this 0.27 by 2 pi, so we're going to multiply by 2 pi, 2 shift pi, and we get equals, it's going to equal period, it's going to be 1.743 seconds. 1.743 seconds. Now we'll see if they want to round it off. Okay, so it doesn't say how many units, how many decimals it wants it to. Now finally, find the length of a simple equivalent pendulum. Simple pendulum has the formula 2 pi root L over G. And we know that if it's the same pendulum, it has to have the same, if it's the equivalent pendulum, it has the same period. So we're going to do is go and square both sides. We're going to get 4 pi squared L over G. And that's going to equal this one squared. You're going to square that number there, and we're going to get 3.0384. We're going to isolate L. So what we're going to do is we're going to get L equals 3.0384 multiplied by gravity. Bring gravity up, and bring 4 pi squared down, and put that all into the calculator. So we're going to multiply by 9.8. And then we're going to divide all by 4 pi squared. And what we get there is 0.75. L is 0.754. So L is 0.754 meters. Okay.